Well, good evening and welcome to AES Melbourne section. Good night to be inside, not a good night to go home. I think we'll all stay the night because it was raining badly when I came in. What was it like when you came in? Is it still raining? Still raining. Okay, now tonight we're privileged in that we've got not one but two experts with worldly experience on the subject that we're going to learn about. The topic that we're looking at now is the technologies of wireless microphones, and that is a very topical and ongoing issue because people will change the standards. So tonight we've got two people who've come along. There's James Waldron. There he is. James was trained as a technical officer in naval communications and weapons systems, so watch out, specialising in RF technology and applications. He's had experience as a technician in the recording and broadcast markets and sales and management roles with Australian professional AV distributors and manufacturers, as well as in the AV contracting sector and covering most brands, including all the ones you know, AKG, Sony, Shure, and particularly Sennheiser. James is presently the product manager for professional and MI products at Sennheiser Australia New Zealand and a member of Sennheiser's global customer development and application engineering team. So hold the applause. The second person is Jason Grbevski. How'd I go?
Close.
Oh, thank you. Jason's got over 20 years' experience in professional audio and related manufacture. He's Sennheiser's product channel manager for Australia and New Zealand, overseeing strategy, training, marketing and technology and product development for the integrated systems channel in Australia and New Zealand. Jason is also a member of Sennheiser's global customer development and application engineering team and worldwide Sound Academy channels. That's a pretty impressive bit of expertise for us to have, and so I'd like you all to take full advantage of that. And also, I'd like you to welcome them here tonight on a cold night down from Sydney, and let's make them welcome. So I'll hand over to you.
Yeah.
I can make some announcements, but I won't.
What?
Thank you. No, you're fine. Thank you.
All right.
All right. It's nice to see some faces from the past here. That some old friends. Thanks, Peter, for the invitation. Long-time friends, David. Long-time friends. John, nice to see you too. So, thanks again for the invitation. We've got quite a lot of ground to cover, I guess. So I'm not going to spend too much time blathering on about all kinds of different things, but I'll show a quick agenda of what we're going to try and cover. A very brief introduction to Sennheiser. A little look at wireless microphone history, and I know that Lloyd had a nice little photo of something that a little bit of wireless mic history he showed me earlier that I was quite interested to see. I haven't seen that one before. We'll cover the current spectrum and licensing situation because all wireless mics, of course, operate under a license. We'll have a look at the development over the years of FM wireless mic systems, and then touch on some of the challenges of carrying digital signals over a wireless channel. And then I'm going to hand over to Jace, and he's going to talk about new applications, the newer digital technologies, and get the crystal ball polished a little bit. And it's a fairly wide sort of a view at the moment into the future, but Jace will have a look at that. I'm keen to try and keep it a little bit interactive if I can. So if there's questions that come along the way, that's great. If they're really hard, I'll dismiss them. So there'll be lots that you guys will know about that I won't. But I'd encourage questions as they come along rather than save them up until the end. So Sennheiser at a glance. So it was founded in 1945 as a family company by Professor Fritz at the end of the war. They basically said, well, you can't be doing that anymore. You'll have to turn yourself to some research that isn't about, defence technologies, if you like. And so he started a company in 1945 in a little building here the farmhouse, and he started making vacuum tube voltmeters. And from there, the company has grown. And so headquarters now encompasses all of this. So there's R&D buildings, there's some manufacturing here. The microphone capsule plant is here. Most of the electronics and the Neumann and other Sennheiser mics are made here. So this is definitely global headquarters for Sennheiser. Jason and I work for Sennheiser. We don't work for an agent or a distributor or anything else. We are part of the Sennheiser team globally. There's about 2,500 of us around the world. All the professional products, so the products that Jason and I look after, are all made either here, just outside Hanover, or they're made in the USA, or they're made in a factory in Northern Ireland, in Tullamore. So I don't know how much work they actually get done in Tullamore, but it's a big whiskey factory just there. So anyway, that's a little glance at Sennheiser. Some of the things that you're probably aware of. So here's our little farmhouse where the company started. They got into microphones because there's another manufacturer, and it might have been Siemens, I think, who had a contract for Siemens or Telefunken had a contract for microphones and they couldn't supply enough, so they were looking for another manufacturer. So they went to the professor and said, could you make some of these? And they gave him a sample. He said, yes, I can make some of those. So he got busy making them and realised pretty quickly he could make them better, and ended up making other microphones. This was one of the first under his own name. They got involved in electronics around 1950. Then 1953 saw the MD21, so handheld omnidirectional microphone for reporters, and that turned into a cardioid version called the 421, both of which 421 is still really popular today, and it's based on that omnidirectional dynamic mic. Actually, just seeing all the coverage of Sgt. Pepper's and Richard Lush's all over the place and everything, you just see all that old footage of the Beatles. So the 421's everywhere in live, and
Very crucial connector.
Yes, that's it. Anyway, along the way, 1957 was our first wireless microphone. So that was the first of the Sennheiser wireless mics. I think there are a whole lot of different manufacturers who came up with a wireless mic around that sort of time. It seemed to be a time where there's a whole lot of technologies came that would make that possible. So that was our first wireless microphone. But the idea for a wireless microphone had been around a long time. Anybody want to have a guess at when the patent for a wireless microphone came about? Any guesses? No? 1935? You're heading in the right direction. But we've got a little way to go. So William Van Cise had his patent signed off in March 1917. So I really like this picture. This just reminds me of Jaime from Get Smart. He's got the little lightning conductor on his head, just like the picture you had, Lloyd. And interestingly, he's also got some grounding plates on his feet. But he has the transmitter on his body. Here's the receiver to a magnetic wire recorder, which interestingly is recording sync sound with the camera. So it's pretty flash patent for its day, probably unachievable in its day as well, but it's a bit of forward thinking. So 1917 was the first concept. One of the very early implementations was in a car. I'm not sure exactly what the use of this was, but all the equipment could fit in the boot. So it's come a fair way since then. I have no idea what you would do with that, but there you go. So the first Sennheiser wireless mic looked like this. Transmitter, little valve in here, and batteries for 67 volts or whatever for the plate voltage, and a wired microphone. Not only does it show you how far wireless mics have come, but it shows you how far marketing and society in general has come, I think. It's an image of the 50s, really, isn't it? She looks like she should be at Caesar's Palace with the smokes and whiskey or something. It's just it's an amazing photograph. Anyway, this is the transmitter. The receiver is actually not a receiver at all. It did receive this signal, which was about 36 megahertz carrier and 1 milliwatt on a single frequency. But what it did was receive that and translate it up into the standard FM band between 108 and 108 megahertz, so that you could then tune in and deliver audio with a standard FM radio. So that was the concept behind this. So interesting little picture into a long time ago. From there, one of the things Sennheiser is really proud of is, and other people might think, good grief, why did you do it? But big musicals like Cats became possible because of the technology developed in the 1040 or 1036 system, as this was. So it was modular, high performance. You could run successfully 24 channels on stage reliably. And so this was the Sennheiser 1036 system was an enabling technology for those big Andrew Lloyd Webber type musicals. And we've gone on and we've been doing Eurovision for 25 years, and it just gets crazier and crazier. So there's some of the big applications that people see. Jason will talk about other applications that are lots of other applications apart from show, I guess is really it. So let's have a look at the spectrum that we use for wireless mics at the moment and what's happened over the years. So the spectrum allocation chart, which ACMA looks after here, goes from 3 kilohertz. I didn't even know that was I guess it is part of the spectrum. I think up the end, the little white block there might be daylight. I'm not sure what that frequency is, but it's a lot of gigahertz. So for wireless mics, there are certain frequencies we're allowed to use. And back before 2014, we had a number of different bands. We shared this block of frequencies in UHF with television. So free-to-air television was in here with us as wireless mics. We also had this piece of spectrum in VHF for television. We shared that with television if we wanted to. And there was a little block up here, the ISM band in 2.4 gigahertz, which we had access to as well. And a little block here in 900 megahertz as well. There's a few megahertz available in that spectrum. So up until 2014, those were the areas where our wireless mics were able to operate in various technologies. The digital dividend came, the restacking of all the free-to-air TV stations, and things changed for us. So now we still have our 900 megahertz here, block, and a piece at 2.4 gigs that's available to us. We have a much smaller part of the UHF spectrum, and I think we still have the VHF bit. So we still have all of this if we wish to. And we have a piece around 1800 megahertz as well. And if I'm not mistaken, there's one more little piece as well. And that's around 1900 megahertz. So there's 2 little blocks in here that are available. So there's bits of spectrum. I think largely we focus here, but there are some other little bits and pieces of spectrum that work well in smaller projects. But this is really the waterfront property of spectrum for wireless microphones. And when we look in here, this is what happened. We used to have all of this, 520 up to 820 megahertz, to share with the television stations. But with the digital restack, television and us got squeezed down here between 520 and 694. And this space up here has been leased off to the telcos. So they had a big auction and leased this off to the telcos. Why did they do this? Anybody want to guess? Money, yes. But what's driving it is mobile broadband growth. So, does anybody have one of these?
No. Who doesn't?
It's our fault. We're driving this. It's the demand for services for this that's driving these spectrum changes. Cisco does research every year, and they look at mobile traffic, how much mobile traffic is going on. So in 2015, every device, on average, took 500 megabits per month download through the air. They forecast in 2020 it'll be 3.3 gigabytes, so over 6 times as much by 2020. So that's a lot. Compound annual growth rate is 46%, so almost 50% more every year. It's growing like mad. And a major driver for this, interestingly, is video. 2015, half of that content was video. They expect by 2020, 3/4 of it will be video. So more and more people watching video on their mobile devices. Well, it's happening. I mean, there's nothing to watch on free-to-air television all that much. I mean, there's some stuff, but you know, it's the landscape is changing in a big way. But rapid, very quickly done. Just so people know, this is what the happened in the Spectrum auction for the telcos. Optus bought 2 10 megahertz blocks. So this is the 694. Down here is where wireless mics and television is. There's a little guard band, because like the Offspring said, you've got to keep them separated. So Optus bought 10 megs here for uplinks, 10 megs for downlinks, and Telstra bought 20 megs here for uplinks and 20 meg for downlinks. This orange bit wasn't sold at that particular auction, so it was still free. They did an auction, had another auction in April this year, and it was sold. TPG took 10 megs and Vodafone took 5. So all of this is now occupied. Well, I don't know if it's all occupied, but it's now at least all owned by the telcos. So if you were operating wireless mics, particularly in this last little 15 megahertz bits from the olden days, you had the old ones and you're still running with them, you'll probably find fairly shortly that's not going to work for you either. So, despite well, it's illegal anyway, but you'll find if you were operating up here or up here, that'll stop shortly as TPG and Vodafone switch those services on. So we really do need to stick between 520 and 694. In the previous times, TV stations were scattered seemingly at random, probably not at random, but seemed to be scattered in frequency, and there'd be gaps everywhere in the different markets where you could always find a free channel. With the restack, it was decided that they would put all the television channels in any particular market all in concurrent channels, so they'd actually occupy a block of spectrum 42 megahertz wide. So in every major market where there is UHF television, it's now done in these blocks. In the major capitals, Sydney, Melbourne, Adelaide, Brisbane, Perth, you still have Mount Cootha here running. You don't have Mount Cootha here. Sorry, Mount Dandenong. Mount Dandenong here is still running VHF television as the major service across Melbourne, and it's in 200 megahertz roughly around down in VHF. But there's infills and other things around town that is all in UHF, and depending on where you are in Melbourne, it'll be a different little block. Some parts of Australia there are 2 blocks used. Gold Coast has 3 blocks, so it can become quite difficult to find a piece of spare spectrum to operate your radio mics. So the landscape really has changed. It's become more difficult for people to run their wireless mics and find free space. Here in Melbourne, this is the digital television channel chart, and you can see the TV stations are here. This A block is VHF. Then there's a block B. This is 6 TV channels. You can see it's pretty empty here until you get to Bendigo. And Bendigo operates in this TV block. So if you want to buy a wireless microphone system and run it around in Melbourne, you're probably pretty free if you buy one that operates in these frequencies. But in Bendigo, you'll run into trouble. So you need to take some advice from somebody who knows, or have a look at at this chart, which you can get online, to figure out what frequencies you need to use. Anyway, we'll have a look at that. So yeah, when you go to the Gold Coast, for example, they've got a block and a half here, and then you go to Canungra, which is only 5 kilometres away. It's got this block and the southern hinterlands here, so the Gold Coast Currumbin area is full of television. I don't know how they're going to run the Com Games there next year, but we'll see. Anyway, Spectrum is more crowded than it used to be. If you'd like some more information, if you go to ACMA, the ACMA website, and search Digital Television Channel Chart, that spreadsheet that you just saw is actually interactive. You can put a site in there and have a look, and it'll show you where all the TV channels are. around that location. So it's quite a useful resource. Digital television channel chart at ACMA. The other useful resource, really useful, is MySwitch. If you just put MySwitch into Google, it'll take you to this website, and it actually shows you, again, you can put in a town or a location, and when you put that in, it'll give you a map with calculated signal strength based on geography and all that kind of stuff. It's really good. So if you really are worried, have a look at MySwitch, and that's a really useful resource. A little helpful tool is Frequency Finder, which is a website that we run, and that'll also help you find digital television channels in any particular location around the country. Any questions on Spectrum? No? Okay, let's run ahead. Wireless microphones. Okay, wireless microphones just use the same radio technology that has been in use by broadcasters and other communication services for decades. As you can see, some of this is still in, well, some of it's in use. That one's in use at my place.
Build it yourself?
Sorry?
Build it yourself?
No, I found it on the street. I fixed it myself though. But anyway, it's basically standard radio technology that gets packaged and designed so it physically suits what we want to do with it and has the feature sets to suit the application. So you have a handheld, so it's a microphone with the transmitter built inside, or a body pack with a little lapel mic, or a plug-on transmitter to go onto the bottom of a microphone. Any microphone becomes a wireless mic then. Or transmitters, mains powered, rack mount devices. So those are transmitters. Antennas, different shapes and performance characteristics, but little omnidirectional, a ground plane, a vertical dipole, log periodic, and a helical antenna in here, so for circular polarization. So different types of antenna, particularly suited to our applications. The helical antenna gives you circular polarization, which helps reduce dropouts. So, well, the people here with FM broadcasting experience? Yeah? Yeah. So, I'm sure commercial FM or major FM is circularly polarized transmission, as I understand it, or a lot of it. Yeah? Usually? Yeah. Which helps with, I think, just reflections and etc. Yeah. And receivers, of course, come as rack-mounted or body pack for in-ear or IFB. This is very hard to see actually, but it's a very small receiver with a built-in XLR, so you can just plug it straight into your video camera, and it runs quite happily. It's very, very compact. Or the other one that you can just clip on a camera. So different physical shapes to suit the application. Frequency modulation has been for a long time the standard way of delivering good audio quality over radio. The nice thing about frequency modulation is it's largely immune to interference from other splats and different kinds of things, certainly a lot better than amplitude modulation. So this has been the technology of choice for a long, long time. There's a number of licenses available under the Low Interference Potential Devices class license, updated in 2015. So these regulations show you the sorts of specifications that we have to abide by in order for our wireless mic equipment, or anybody's wireless mic equipment, to meet the regulations. So in the VHF area, we're allowed 50 milliwatts, and we can occupy 330 kilohertz of bandwidth maximum. Up in UHF, between 520 and 694, we can have frequency modulated with a bandwidth of 330 kilohertz with 100 milliwatts. And then they added the digitally modulated signals in the same bandwidth, again 100 milliwatts average power and a bandwidth of 330 kilohertz. There is another license here for 1785 to 1800 megahertz as well. again with 100 milliwatts. So the main thing I want to point out here is that there's an amount of bandwidth we're allowed to occupy, and it's not great. Consequently, there are some limitations in terms of the actual performance you can get. And while in Australia we're allowed 330 kilohertz, we also have to comply with the ETSI standards, which for most of the energy is only 200 kilohertz wide. So we really have to fit within 200 kilohertz of bandwidth for most of what we're doing. And that gives us some limitations, particularly in terms of what we're able to deliver audio quality wise. Which brings me to Mr. Shannon, who some of us will have heard of, I'm thinking. The father of information technology, and a man who made some very important, I guess, discoveries and theories. There's a bit of, I'm sorry for the heavy math here, but basically you can put more data down a channel that has greater bandwidth and better signal to noise. The analogy of this is sitting in a noisy pub, trying to have a conversation with somebody. And so if there's no noise and if it's quiet, you can have a conversation with somebody pretty well, and you can speak pretty quickly, and people, you can have a good conversation going back and forth. As the noise level rises, it becomes more and more difficult to have that conversation. And one of the things that you can do to improve the conversation intelligibility is speak more loudly, so you speak over the noise, but also you might find that you have to speak more slowly, so you take more time to deliver the same information to the person. You might even have to say it twice to overcome the noise. So it's the same thing with Shannon's theory. You can deliver more information if you have more time, which is kind of like more bandwidth, and if you have a better signal to noise ratio, so if your noise is low or you've got a louder voice. So that's really the nub of this. This just gets more and more technical now, I'm sorry. But the idea that Mr. Shannon had was you can deliver more information in a quiet communications channel or a broad one. So the corollary is if you narrow the channel and bring up the noise, it's really difficult to get a lot of data down it. So there's because we're limited in the bandwidth we have, right? We have to meet these restrictions. Then there's a certain amount of physics that says you can't get better performance than this out of that little channel. So there's a number of techniques employed over the years, from the very beginning of the Nady systems and what we had in 1957, to improve audio performance. There's a couple of techniques used to improve signal-to-noise ratio. They're commonly used in broadcast, commonly used in all kinds of different places, in record players and tape recorders and everything. Pre-emphasis and de-emphasis. So on transmission, you emphasise the high frequencies, because high-frequency noise can be quite annoying. So if you increase your high frequencies when you transmit them, in the receiver then you can filter and reduce the amount of high frequencies. So you end up with a flat frequency response for what you want, but you've actually reduced the noise. The high frequency noise has been filtered down to some degree. So this technique is employed in wireless mics just as it is in commercial FM broadcasting and lots of other places as well. Standard technique. So this is something that's been employed. One of the other techniques that came in a little bit later on, after wireless mics were getting more and more common, was this concept of a compander. And so because of our bandwidth limitations, we have something like a 60 dB dynamic range or 60 dB signal to noise ratio available in the channel for us. But we'd really like a lot more than that. We'd really like to have this big dynamic range available, maybe 100 dB. But how do you squeeze, and squeeze is the word, that into here? So you use a compressor to compress that initial dynamic range to fit down our skinny radio channel, and then in the receiver you expand it back out. And dynamic range is the right word to have here, so you can have your 100 dB dynamic range back at the receiver. Obviously the signal to noise is no better than 60, but the dynamic range can be there for you. So this is one way of improving the audio performance and the sound that you get through a relatively narrow dynamic range in the channel. I mean, it's the same thing. These sort of techniques have been used in all kinds of different places, and I go back to tape machines and Dolby and DBX noise reduction. It's a very similar sort of concept here that's used in wireless mics, in FM wireless mics. Different brands are not compatible. Of course, compressors and expanders, there's all sorts of attack and release times and etc., etc. So different brands are not compatible. In fact, even within a brand, different models are not compatible either quite often. Some systems have companders that are implemented in DSP rather than in analog systems. And of course, digital is fantastic. So if your marketing department can get the digital word in there somewhere, it's going to be a much better, it's got to be better, right? Anybody who's looking for, it's a digital, will have that one. So sometimes systems with some DSP are marketed as digital. So pay attention carefully when you're looking at that. There's not a lot more to say about that, but that has made a big difference to audio quality in wireless mics. One of the next things that came along, and again, if you well, probably didn't notice the antennas, but on the early wireless microphone systems, there was one antenna. And of course, the transmitter sends out signals. It doesn't, the antenna is not like a magnet that draws all the signal to it. Your transmitting antennas that throw stuff everywhere, and at your antenna, you get a sea of reflections and direct signals. And as your transmitter moves around or other things move around in the room, it's quite possible that the sum of the direct signal and the reflected signal at this particular point become not much or not enough to sustain reception, and you get a dropout. So the concept of diversity, again a technique that's often used in communication systems, came to play in wireless microphones. So you put up another antenna in a different place, and the chances of the sum of the direct and reflected signals adding up to not much here and not much here at the same time is very, very low. So the receiver just picks the strongest signal from each antenna, and that can give you significantly better reliability in your reception. So it's a really important technique that made wireless microphones much, much more reliable for people. Okay. Questions? No? Okay.
Question, just about diversity.
Yep.
Do you do that space diversity? Do you ever do frequency diversity, or that's just too tricky given the band?
That's too tricky for me. Jason will talk to you about frequency diversity. But yes, frequency diversity happens too.
Okay.
I must say there's one of the other manufacturers, also starts with S and made in America. They have a system that does offer the concept of frequency diversity, so there are two carriers in the transmitter being transmitted.
That's it.
Yeah. I won't get into the pluses and minuses, but
That's complex.
Yeah. So you have two carriers there instead of one, and the receiver can choose either one.
Yeah.
Yep, that happens for sure. And time diversity is another one as well. All of those come into play. Okay, here's a drawing. So this is the RF signal over time of one particular antenna, and you can see here you'll have a dropout when the signal gets really low here. For the other antenna, the green one, you would have a dropout here if it was only this one. But by using diversity and picking the best signal all the time, you can get quite a good signal all the time and avoid any potential dropouts. So diversity is a really good way to improve reliability. One of the other challenges with wireless mics is intermodulation distortion, not distortion, that's a different topic, intermodulation products. So when two transmitters get close to each other, they interfere with each other, because if we think of the output amplifier in our transmitter and our antenna, this is not only a good transmitting antenna, this also works as a receiving antenna. So signals picked up from another transmitter can come back into our transmitter and upset this output stage and make it operate in a non-linear mode, and generate harmonics. And so now what we find is when two transmitters get close to each other in space, or they're really powerful, you can end up with an extra frequency generated from, where did that come from? Nowhere. The laws of physics have got you by the short and curlies, and you end up with all these frequencies in the air if you've got a lot of channels running that you didn't really start with and you didn't know were coming. So how do you make sure that you can be operating more cleanly? One of them is planning all the frequencies you operate on, but it'd be nice if you could somehow stop the other signal getting back up here and upsetting this. And so there is a way that you can do that by putting a device called a circulator in the output stage. And so the circulator only allows signals to flow in one direction and out the next port. So now we can run equal channel spacing and get more channels stacked up within any particular frequency range. So the concept here is that the signal from our amplifier goes into the circulator and comes out the next port and up the antenna, transmitted into the air. Beautiful. But any received signal that comes back in here also goes into the circulator. It's like a roundabout really, but you have to leave by the next exit. So this other signal gets picked up by the antenna, comes in here, but gets shunted down to ground, never gets a chance to get in here. And so we're able to operate with very, very minimal intermodulation generation. Intermod products are reduced somewhere around 40-50 dB. So this is a very effective way of reducing intermod products, which are a real challenge to wireless microphone planners. So those are some of the techniques that have been used over the years to improve the state of the art in wireless microphones. And in FM systems, that's about where it's got to. Then the world goes digital. It's been an exciting time since whenever that was, 1980 something. And there's a lot of reasons to go digital, right? It's better quality, all the analog issues go away. It's a lot easier to operate. You don't really have to do anything. You just plug it in and it goes. You can just do a quick software update. Perfect. And it's cheap. Always it's cheaper. So these are all the good reasons to be digital. Of course, logic, it's the next step. Like, that's where you're going, right? You want the new one? I'll have the digital one. Of course, it's always better. Life's better. Yeah? Well, yeah. That's kind of, I don't know, marketing sort of stuff, I think. But these are the expectations that are presented, and as we all know, it's not the complete picture. Some of this is true, but it's not the complete picture, and there's pluses and minuses each direction. So, some of the goals of getting digital audio over wireless is much improved audio quality. Get rid of those compander artifacts, because the compression and expansion can create pumping sort of sounds, or if you get a plosive sound on the mic, it can really upset a companding system. You get much better signal to noise and a great frequency response. But Mr. Shannon's shadow is here. If we'd like 24-bit 96 kilohertz digital audio to be transmitted, when you do the maths, that's about 2.3 megabits per second. If you're thinking you might like something like CD quality, or even better, 18 bits at 44.1, you end up around 800 kilobits per second. So there's a big difference between, wouldn't that be fantastic, to, well actually, this is pretty good, and it's probably good enough for most wireless microphone systems. By the time you put some more data for framing and coding and all of that sort of stuff, the extravagant one ends up at 3.5 megabits per second, and the more realistic at about 1.2 megabits per second. However, we've only got 200 kilohertz of channel capacity, so how do we get all of these bits into that little narrow channel? It's a challenge. It's a challenge. So, some digital modulation. This is going to be hard. So in order to get as much digital information onto a radio carrier as possible, one of the techniques is to modulate amplitude and phase together. So it's no longer a simple frequency modulation. We have to modulate amplitude of the signal and its phase in order to be able to carry lots and lots of data. And so, if you have, say, 4 states, who put this in? I might just go back there to the finished slide, I think. So, if you've got a bit stream running along with 1s and 0s, and you imagine you have 4 different phase angles that you're going to use to carry either 0, 0 or 1, 0 or 1, 1 or 0, 1. Now we can get 308 kilobits per second because we've got 154 symbols per second, but each symbol represents 2 bits. So by having these 4 different states, we can double the number of bits that we transmit as opposed to the number of symbols. If we make this more complicated and put some amplitude modulation on here as well, and maybe have some more phase angles, then instead of 2 bits for each symbol, we can get more and more bits per symbol. So here's a little chart that shows you, for example, phase across this way and amplitude up and down. So if you have a symbol that says the phase is -3 and the amplitude is +3, it represents 4 bits. These 4 bits, 0010. If your phase is -1 and your amplitude is -1, it represents 0101. So now we can have a number of different phase states and a number of different amplitude states, and each of these now represents 4 digits. So if we make this more and more complicated, each symbol can represent more and more bits, and we still have a limit. We can still carry a certain number of symbols within our bandwidth. So within our 200 kilohertz bandwidth, we can still send enough symbols if they're complex enough to carry enough bits to get to the end. This is not a Sennheiser invention. This is how digital television gets transmitted or gets modulated as well, and lots of other stuff too. It's complex, but it works. Do I need to say some more about this, or is it no? It's a complicated modulation technique to allow you to get lots of bits into a narrow channel. And if you want to send high quality digital audio, you need to do it this way. Otherwise, you're not going to get enough bits to get the audio quality that you want.
Sorry, just the more complicated you make that, does that begin to introduce latency or any process?
Not particularly latency. It doesn't have a lot of impact on latency. What it really has an impact on, though, is that it gets harder for the receiver as the noise floor comes up. It gets harder for the receiver to tell, is the symbol here, is it this or is it this one? So as the noise sort of grows and makes this more fuzzy, it gets closer to this one, and then the receiver has to be able to determine whether is it this or is it that. And so you end up needing a really strong carrier signal over the noise in order to deliver reliable performance. So, and there's where Shannon comes back in about noise. You need to have a signal that's much bigger than your noise in order to get lots and lots of data through. So there's the challenge, because basically what you're doing by putting more symbols per second, you're making all of these closer together, because now you're trying to fit 6 by 6, for example, into this same space. So they're all kind of closer together, so they can't really deal with more noise, because now the receiver's going, is it that or is it that? Not sure. Can't really tell where, if you get a bit that appears here, for example, is it this one or is it that one? So as you jam more in, they get closer together, and you need more signal to noise in the RF domain in order to be able to get a good demodulated signal. And that means you start to reduce your range. Is that where this goes? Yes. Kind of. So, that sort of comes back to the budget. When you're designing a product, any product really, you have a budget. And the budget's not just about money. In wireless mics, it's about how much audio quality do you want, how much battery consumption, how much power consumption can you deal with, how much heat do you have to be able to dissipate, how much can it weigh, how big can it be. All of those things provide you with budgets that pull you in. Anybody designed in product development or design knows that there's budgets trying to pull you in every which direction. And so I guess the basis of it is that you can build any sort of a device, really. The limitations are given by the regulations and the physics. They're sort of the boundaries that you have to work within, and they're the same for everybody. And you can make a certain set of compromises that make sense for any particular use case. And the wireless microphone that you use for Eurovision might be a very different one for the one that somebody's using for news gathering, running after Alan Bond down the street trying to get an interview or something. Or it might be a very different one for the one that a blogger is doing some blogging thing on the web or whatever. Maybe they don't need the same wireless microphone that somebody does for Cats or Kinky Boots or whatever the show is that's running at the particular time. So a certain set of compromises can be optimal for one use case but never for all, because all those things pull you in different directions. So we built a thing called Digital 9000, which is the pinnacle, and it allows for the full transmission of 18 bits at 44.1 kilohertz sample rate, no data compression, no nothing, full transmission of high quality audio. But it also has another mode with some data compression to reduce the number of symbols per second that it has to send, which means that it can deal with higher noise floor in the RF domain and still deliver good audio quality. So that gives you a longer operating range with a minimal impact on audio quality. So for different compromises, you sort of need to have different system designs. Oh, product picture, sorry. That's 9000, pinnacle of wireless technology. And if anybody saw Adele or Taylor Swift or people like that, they're on these. This has translated into a new model called D6000, which takes all of that technology, condenses it down into 2-channel receivers for production and rental. So that's kind of got to the state of play as it currently is in terms of FM wireless microphone technology, the developments that have gone into that to get it to the point where it is today. And it can be very, very, very good. It can be as reliable as all get out, and audio quality is just exceptional. If you want to go to digital, then this is the place where the technology starts in terms of the top quality, reliability of reception and audio quality. Seriously, you cannot go past the quality that this delivers. Regardless of the brand, it's actually the technology inside. Nobody else does stuff like this. But not everybody needs this for their use case. There's actually more than one way to skin a cat. And I did go looking on Google for a picture of, I thought, I'm bound to find a funny little cartoon about skinning a cat. But when I put skin the cat in Google, it was very gruesome. So instead we have 2 one-way signs. It wasn't very nice at all. So I'm going to introduce my buddy. Oh, I should ask, before I introduce Jace, are there any questions on the ground that I've covered so far? I don't know whether it's the sort of information you're looking for, but that's where I've gotten to. I'm sure we'll be here for some questions later, but I'm going to introduce Jason, and he's going to tell us a little more about where to from here and other use cases and so on. So I'll hand it over to you, my friend.
Thank you, James. Give me a round of applause. Thank you to all for having us here today. It's a good opportunity for us to sort of rub shoulders and get to hear what your experiences are, but also to sort of show you the direction in terms of where we're headed and where we see the industry pushing the product technology. And it's very much a case of the users starting to drive where the future ends up, rather than the engineering teams thinking up these magical products and then finding somewhere for them to be used. And it's a bit of a paradigm shift in terms of the way products are designed. And it's something we as a company have had to adapt to. But it's definitely a focus for us in terms of the way we look into where these new horizons are. I suppose to look at where we're going, we have to have an idea of what is the need that we're trying to satisfy when we look at developing new product. It's probably the key thing is defining who we're making things for. James has sort of iterated on this point where one product doesn't necessarily fit the form factor for every use case, and so having a better idea of who those users are of our products is pretty important. In terms of the traditional users of our product, this is kind of well established. So, performance in theatre, broadcast and news gathering, corporate presentation and AV, and education markets. From a user of wireless microphone products, are very well established. The adoption is quite high in those particular sectors, and it's something that technically they're able to deal with. But what we have moving forward is a new breed of users and emerging user groups that are really not from the traditional spaces. And they include things like amateur filmmakers. And this is kind of spawned from this whole revolution of DSLR, indie filmmakers, and it encompasses people from small independent film students through to wedding videographers who are starting to bring narratives into their storytelling. But it's opened up a whole suite of users that are essentially prosumers, in the fact that they may have some technical background. Generally, it revolves around video or image acquisition, and not necessarily in terms of audio skill set. So what we need to do is look at how we produce products that perform reliably in those situations, especially when we're talking about events where time is critical and there's no way to relive that moment. But it also needs to be quick and easy and simple for someone who doesn't have the understanding of spectrum and signal chain and gain structure, and how we create products that cater to those types of users. This kind of brings the vlogosphere into play. And these are content creators that start off as amateurs, posting videos on how-to or their experiences or their reviews of products on YouTube and Vimeo. But eventually there comes a time where they build up loyal fan bases and they start to monetize that content. And from there, the desire to lift their production value, to keep those users coming back and looking at their content becomes important. Lifting production value means investments in equipment. Part of that equipment is acquisition of audio, and again, looking at products that are catered to them, that give them the mobility to be able to sort of acquire audio with varying degrees of flexibility in terms of where they position themselves. Mobile journalism is a huge space for us moving forward, not only for us, but I'm sure for all wireless microphone manufacturers, is the fact that we have these devices that are incredibly powerful. They can acquire image, they can acquire sound, and then upload that into this miraculous thing called the cloud. Everybody sees it instantaneously. But it also brings the accessibility to news closer to the user themselves. So by having these people at the edge, they can then be at the scene much faster. And generally they are not professional users. They're journalists who have been given a tool that they can now acquire video and audio at the scene rather than just document the event. And corporate and collaborative environments. So the nature of a traditional corporation where they have a large meeting space or a video conference suite is slowly being disbanded. We're seeing more and more smaller collaborative spaces where anywhere from 4 to 10 people will meet up in a small space, And generally those spaces are flexible in nature in that we don't understand what the setup of the scenario will be in that room from one day to the next. Could be used for a product launch in one session, or a video conference in another, or a brainstorming session on new product development. So wireless technology gives us the ability to sort of move around that space and allow them to still have coverage of that spoken word in a dialogue with a far end or a conference call, for instance, but then have the ability to be mobile within that space. So where to from here? I guess the spectrum thirst is something that is not going to waver. We have an issue where that the amount of spectrum that we can play in is diminishing, but our requirement for spectrum is continuing to grow. So what this graph kind of represents here is a bit conceptual rather than hard data, but it's showing that we start off with a position where we have ample spectrum and a demand from using wireless technology is quite high, but we have a law where that amount of spectrum is slowly being diminished, but the demand for wireless is continuing to grow. As that demand builds and technology develops, the number of connected devices that we then have using wireless technology grows at an exponential rate. And we'll go into that in a little while, but basically all the devices we carry on our purses over the past 5 to 10 years has grown significantly in terms of connectivity and use of spectrum. And that's not going to get any better. So we as manufacturers need to adapt in how we use spectrum more efficiently and also where we play. The difficulty we have is from a global perspective is that those spaces are not the same in all regions. So how do we look at standardizing as much as possible, but still being able to cater to the regulations within each region? Unfortunately, the sell-off of spectrum will continue. For governments, it's an easy way to fill the coffers without much cost or outlay on their behalf. So it's an attractive way to balance the budget, especially when there is demand and they're paying top dollar for that piece of air. So that won't go away. But the real cost is, what does it do to us in terms of use of wireless microphones? And that affects things not only but business and collaboration and education, but also the cultural events that are handled by wireless technology as well. How do we impact our ability to keep the cultural activity going on within these regions globally as well? So I found a little animation that illustrated very effectively how the thirst can never be quenched, basically because we are our own worst enemy and block our ability to quench. So I guess to look at how we deal with these solutions now is to have a look at the spectrum we play in and what the devices we create can basically perform, or what functions they can perform within that spectrum. And it tends to be different because, as James sort of covered, there are costs to playing in each one of these spaces. And if we're conscious of what those costs are, then we can design a product that lives in that space, that fulfills that particular function, and those costs are sort of acceptable in terms of the performance of that. So at the moment, in terms of new ground, we're covering 900 meg, 1.8 gig, 2.4 and 1.9 gig, and I'll kind of go into those. So 900 meg is an industrial science and medical band. And it's license free in Australia. And in the US, it's 926 to 928, the space we can play in. And it allows us to do some efficient use of spectrum within that space. The noise floor is reasonably low, but we do have some issues in that it's not something we'd suggest for mission critical applications. Partly because some of the regulations requires that their transmission power it maintains sort of low output in that space. So it lends itself well to things like tour guides systems where close proximity in terms of a presenter running a tour with a mobile transmitter and a group of visitors on that tour that are in relatively close proximity. So our transmission power is limited to 10 milliwatts in that space. So not great, even though the noise floor is reasonably low. It doesn't afford it to sort of overcome strong interference or to get above a serious noise floor. Also, that amount of spectrum is not great. So for Eurovision or a performance, it's not the kind of spectrum we want to play in. But it has its place. 2.4 gig, we all know this piece of spectrum. In Australia, or actually globally, we're 2400 to 2438, and it's an ISM band that is license free globally. There is some change in regulation in terms of hopping and non-hopping in the implementation globally, but essentially it's a similar structure. But we share the spectrum with a multitude of other devices, right? So there's a lot of people on this train. And that's everything from Wi-Fi, which is the biggest culprit, but that's Bluetooth, that's microwave ovens, that's your wireless keyboards and mice, and a bunch of other products. You know, it's wireless flash triggers and things like that that all operate in that spectrum. They can coexist, but there are costs to living in this space. So we use multiple carriers changing frequency, and we employ frequency shift keying modulation. So basically, changing frequency to represent the bit stream. We can do some smart things in terms of mitigation over interference in this space, in that we can run redundant audio streams, so that if there is interference on a primary stream, then that primary can hand over to the secondary. The secondary will then take over the role as primary and find another free piece of spectrum. So it's a spread spectrum technology where it's hopping around within that space. But in order to get reliable transmission, we're occupying two pieces of spectrum to ensure reliability, partly because of the amount of congestion in that space. So efficiency in terms of spectrum from a wireless transmission perspective doesn't afford us the ability to grab really high channel counts like we could with UHF or other technologies. But the attraction is, from a global perspective, is I can travel anywhere with my 2.4 gig device and essentially know that it's going to work in that space without having to run into license issues or know that I'm going to be interfered with by some other product. Latency depends on the system design. So for us, for example, we have our Wireless Evolution D1 product that lives in this space, and it has a latency of about 3.9 milliseconds, which is fine for performance situations, but other pieces of spectrum potentially have higher latency, but afford us other benefits, which I'll sort of run to in a second. In terms of transmission power, we are limited to 100 milliwatts, which James alluded to a little bit earlier in this space. So as we're moving to shorter wavelengths as well, our ability to overcome obstructions by physical, body pack sitting on a person, turning out of the range of coverage of the antenna, even though we can employ diversity techniques, the ability for physical structures to interfere with transmission is much higher in these spaces than it is with UHF. And that's part of the attraction of UHF as well, and remaining in that spectrum, is it does give us the flexibility to make mistakes, and it still will operate reliably. So there's no shortage of products in this space that don't use Wi-Fi standards but still live in this spectrum. Examples from us is the Wireless D1. We have a wireless conferencing system, and it's not only us, there are many other manufacturers that do delegate conferencing systems that live in this space. And our tour guide product, the guide port, which was used for the David Bowie exhibition, all lives on 2.4 gig. So they don't use Wi-Fi, but we employ that same channel structure in terms of delivering our audio signal over that piece of spectrum. what it does mean, it requires a little bit more coordination in terms of those other parties that are using that space. So from a performance perspective, if I was using that wireless mic in a pub, there may not be as much interference in that 2.4 gig spectrum as there would be in, say, a corporate environment. So a corporate environment, 2.4 gig operation would probably be a bit hostile for a reliable operation for a wireless mic. But with a little bit of coordination with IT departments, for instance, we can see where they're positioning their access points and whether they can lock those into fixed channels, and then we can, or other providers can find ways to live and coexist without interference in those spaces. Any questions on that so far? What I haven't covered here is the 1800 meg band, which we employ with our Evolution series. It gives us similar performance to UHF, but obviously the higher frequencies gives us those issues in terms of dealing with obstructions, but the noise floor in that space is much lower. So the reliability of transmission, even though it's lower power, is still quite good and comparable to what we're experiencing in UHF. DECT. Anybody know of DECT? Yes? Cool. So DECT for us is a new space we're playing in. Basically, product's been working for us in the last 12 months from a wireless microphone perspective. DECT stands for Digital Enhanced Cordless Telecommunications now. It used to be Digital European Cordless Telephony. And it was a standard that was set by Etsy back in the early 90s, and primarily revolved around telecommunications. So there are literally tens of millions, if not hundreds of millions, of DECT products out there, from baby monitors through to cordless handsets and telephones, both in domestic and commercial applications. But it's the most successful wireless standard next to Wi-Fi in terms of adoption and deployment globally. It's heavily regulated in terms of how you structure the use of your products within that spectrum. It must comply to the DECT rules, and that affords a very standardized approach in terms of different manufacturers having products coexist in that space. The DECT Forum manages the standard, and its members are made up of a suite of companies that are very much outside our industry. And they are heavily invested in continuing to see this standard move forward. So the good stuff with DECT. It gives us high capacity and structured access. So our ability to get higher channel density in this space is very attractive. It's flexible in terms of its addressing and security. So it uses things similar to a MAC address that a network has, where each device has its own unique ID. Each device has its own DECT ID, and that is an identifier that is unique to that device. There are secure transmission methods that happen between a fixed part and a portable part that ensure reliability of that connection, but also the security of what's being sent over that link as well. Very high spectrum efficiency, and I'll go into sort of how we do that in a second, but it's very reliable. Its ability to deal with interference and how it mitigates any interference that's observed is very robust. And that's not something that we employ, it's across the standard itself. And the ability to basically change the amount of data we need to send in a payload. So the ability to aggregate what's part of the standard to create bigger blocks of data that we can send depending on the amount of information that needs to get across in that spectrum. And the other is power efficiency. We get really great battery operation in wireless products in this space, up to 16 hours, as opposed to the normal 6 to 8 that we see in UHF-based products. The other thing is it's tried and tested. So while we're late adopters in terms of using this spectrum for wireless mic technology. All that legwork has been done before we've come into this space, so it's very robust, very sound. All the kinks have been ironed out. But there is no free lunch, and the cost of all these great things, one is latency. So latency within that DEC band is quite high. Part of that is to build a buffer in so that devices, if they do see interference, can have a structure to go and find a new place of playground to play in without interfering others. So it's a coordination angle that's taken there. But obviously that doesn't translate well into things like performance, where we need to do any monitoring or IFB. The latency in this DEC spectrum is not really favourable to those applications. But there are other applications where there's not so much of an issue. Things like conferencing and audio for video acquisition. The other downside is it's a mutually exclusive connection. So we have a one-to-one point pairing that happens with DEC devices. So we have a fixed part, a portable part, and their link is established, and basically they talk to each other and nobody else. While that supply gives us secure transmission, what it doesn't allow us to do is multicast that audio transmission in the way that we can do with UHF. The other thing is, from a compliance perspective, we don't have that same level of flexibility with DEC-based product that we do with traditional UHF and VHF transmission. We can't do the complex antenna combining, amplification and distribution that we can in those parts. We can do some passive combining, but essentially that's all we can do in that space. So that becomes a hindrance where we need larger coverage areas or spaces that are greater than within the range of coverage of the receiver system itself. So as long as we know what those limitations are, then we can build systems and products around catering to those needs, but understanding that this product may not necessarily lend itself well into this environment. I'll brush over this fairly quickly. So it uses a frequency shift keying schema. So essentially what it does is the Gaussian filter is a smoothing filter that allows tighter spacing of the modulation so that we can be more spectrally efficient in terms of how we're transmitting signal. We use a time division multiple access method. So the signal transmission is broken up into frames. Each frame is 10 milliseconds long, and within that frame there are 24 time divisions. And each one of those time division slots is made up of this basic structure. Okay, so our frame basically gives us 10 RF channels as well as those 24 time division slots. And a link can live within either the uplink and downlink. So the frame is generally broken up into an up and downlink of 12 time divisions, and a link can coexist in two different frequencies, two different RF channels, or within the same RF channel themselves. So what happens is each device basically scans the spectrum when it turns on. It creates a table of available time slots within that spectrum, and it says, okay, this position is free, and I'll take up my domain within that space. And it's running that scan of the spectrum table every 30 seconds. Each device is obliged to do that. So what it does is it constantly knows what other time divisions are occupied, and gives the system the ability to then have an idea of, if I do have a disturbance, where I can move to an interference-free position within that spectrum. So the slots are made up of this structure. So the S field gives us the sync, and that gives the ability for those devices to understand where the time movement is. The link control is something that becomes important when we look at how devices can coexist with each other in terms of higher quantities. and it covers things like our master-slave relationships and how that is managed across like devices. The B field is essentially the payload, so that's carrying the audio signal, the spectrum indexing table, and any additional changes that will happen if it finds interference. And then we've got some cyclic redundancy checks at the end and a bit of a guard timer to allow some buffer there. So this is happening within each one of those time divisions. The master-slave structure is essentially a two-level system. So if I turn on one device, it will, if it doesn't detect any other devices, it will become the master. And essentially it is the clock in the system. So any other devices will look for a master. If they find one, they will then take the level 1 or level 2 slave or follower systems. So in the event of a master falling away, one of the level 1 followers will then take up the slack and become the master in that situation, and the cycle continues. So it's incredibly robust when we've got like devices coexisting with each other. So a scenario could be for our AVX product, to give an example. It's for, it was that small receiver system that James showed in one of his earlier slides. So it straps into the camera, used for news gathering, for let's say for a press event, and we may have 12 or 13 of those systems operating with different providers, different operators, not coordinating with each other. They will detect each other's presence, and one will become the master and provide synchronization clocking to all those other systems. Right. So what that means is that if there is interference, they will all dance to the same tune and not collide with each other. So this idea of awareness of other devices that are operating within that space is really where the future brings us the ability to have larger channel counts coexist. Does
that cover a range of manufacturers?
Yes. So that is, well, that syncing is like within the manufacturer itself. The collision avoidance is within the DEC standard, but the synchronization is within the manufacturer itself. Yeah.
So I think so it could coexist with baby monitors. And
totally. Yeah. Yes. Yeah. So where they may use a smaller time division or only a single time division because it's lower bandwidth data that they need to send, whereas ours may be full bandwidth 2020 audio transmission, which may use 2 or 3 time divisions. So our congestion of that space may be greater than something like that, but they will all coexist within that same spectrum. So each device in that DEC band has the ability to live anywhere within that DEC spectrum.
There's echoes of Lab B, Lab D in networking and ISDN in the frame structure.
Okay.
So that's its history.
Yep. I have kind of covered that already, I guess. Okay, so the process of jumping frequency tends to be initiated by the portable part because it's likely to be the device that encounters interference first rather than the receiver. The other distinction is these are all transceiving devices, so there's back channel communication between them as well. And this is all happening over the air, right? So that's within the DEC transmission itself. So there's another consideration that we look at if we move forward and these receiving devices, say in an installation for instance, are all connected on the network and visible to each other, is that does that then provide us another layer of coordination because they have complete visibility? And that's really where the future looks at what we can do to sort of have smarter devices that are reporting to each other where they are. In terms of the types of products that use DECT in commercial environments, so we have our Team Connect Wireless, which is a modular conferencing system. It allows for connection of mobile devices and PCs for conferencing applications. Each one of those modules has a loudspeaker and microphone capsule built in. but it uses DECT to transmit both the far end and the receiving audio between those master and satellite stations. Again, they can coexist in really great numbers. It's the same transmission that allows us to do 400 call center headsets within a call center floor that coexist quite happily with each other. We also have the ability to throttle the RF power on these devices as well, so that in a situation like this, and I had a receiver that lived in the lectern, I really don't need coverage of the entire space. So by throttling that RF strength, I'm providing or creating less pollution within that environment. And so when we look at coexistence, it's really what I'm doing in this space, and it doesn't have much bearing on the adjacent space. So you then have the ability to run potentially hundreds of channels in a larger installation that you traditionally wouldn't have been able to do with normal systems. And so the AVX product in our Speechline Digital Wireless use that DECT spectrum. Again, these are quite specific in where we've created the application. So this is for presentation and corporate AV. Again, latency is not so much an issue in that scenario. Audio acquisition for video, similar sort of thing. Yes, James. Sorry.
What is the latency, James?
So we are at approximately 19 milliseconds end to end. About 16 milliseconds of that is the latency embedded within the DECT standard. So it gives devices a buffer to be able to sort of hop around without, running into each other.
So for video, it's half a frame.
Half a frame, yeah. Any questions on that side? No? I think I've kind of covered most of this. So the handover method, unlike the 2.4 gig spectrum where we have a constant... Yes, sorry, Graham.
Sorry, I wasn't asserting. There were two parameters there. Where are you up to with the bandwidth and the dynamic range for the DECT systems relative to your production systems for microphone?
Dynamic range, I have to check, but last, I think we were at 98 dB on the DECT. Yep. And bandwidth was 20 to 20. So
what about the telephony products that you don't sell? The telephony products are down.
Oh, absolutely, yeah. So things like that wireless collaboration product, that we're looking at 11K for that, which is wideband speech for as far as telephony is concerned. The call center headsets would be looking at 7K. So again, it's horses for courses. Is the benefit of going to wider bandwidth? The data transmission rate will reduce the number of links that they can have within that one space. So they're those trade-offs that need to be considered. But again, if we're looking at applications, then we can deal with those trade-offs and see where they're acceptable and where they're not. So that handover, we're with 2.4 gig, we have a redundant transmission going on so that if there is interference, that one takes over. With DECT, we don't. Part of that is so we're not polluting the spectrum. But if there is interference, what will happen is that new time division is consumed. Once the system establishes that that is robust and not falling away, or there's no interference there, it will then let go of the other time division and free that up for use for another device. It's not as fast a failover, so there may be dropouts that are heard in those situations, but generally the way it deals with that interference is really robust to start with. And we can do clever things by shaping the way those dropouts are represented. So when error correction runs out, we employ a mute algorithm so it rounds off that audio dropout quite smoothly, so it's not as perceptible mid-speech.
Like a crossfade.
Yeah. So where do we go tomorrow? That's very much where we're at today in terms of what's real physical product that's existing and working. But the thirst for network devices is continuously growing, and it's not only from us as consumers, but it's also from industry, with the the requirement to have more telemetry coming back from manufacturing, from retail, from all those sorts of environments that are basically wanting to use more of that spectrum that needs to be sold off. So I did a bit of a quick count when I first built my home back in 2004 as to the number of wireless devices I had on there. And count was very quick. I had 2. So a couple of laptops that were using 802.11b network. And then I did a count last night just quickly as to the number of connected devices we're running at home now. Any guesses? Any ideas?
17. I had 17. 14, 17.
That's 17.
27. Wow.
Right. And that's nothing crazy. Basically, it's a bunch of mobiles, it's some AirPlay devices, it's televisions, it's AV receivers, it's basically lots of stuff. Tablets, PCs, home theatre PCs. And we haven't even started to look at, Wi-Fi connected lighting or, personal home assistants and things like that. So you can see the amount of swell that's happening within this space. And then once you look at a commercial environment, it's even more drastic. So the amount of pollution and congestion in this space is only getting worse. So where does that leave us? So these are things we kind of need to consider. 802.11n and AC are well established and they're with us now. Most of the modern devices will operate within this spectrum, and that's sitting in 2.4, 5 and 5.8 gig. So that's nothing foreign to us. Basically the move to 5 gig was because 2.4 was too busy, and it gives the ability for higher data rates within that space, but obviously shorter transmission distances. Now that space is, quickly becoming congested, and there is a need for higher bandwidth data for things like video streaming, and that running not only through the home but in the corporate environment as well. So the ability to have a laptop just walk in and stream its presentation wirelessly to the display device is becoming more and more commonplace. And so the 802.11ad standard is being ratified and brought in, and that brings 60 gig transmission. Only very short distance, but high bandwidth. So that's somewhere else that's not so much going to affect us, because that piece of spectrum doesn't really do anything attractive for wireless microphone users, unless you're sitting at your desk and right in front of the PC. But this cursed Internet of Things that is dawning upon us is going to create even more turmoil, in that they're going to look at consume the spectrum that we're already coexisting in and been squeezed out enough as it is. So this not only looks at residential environments with Google Home and Amazon Alexa and all the other connected devices that come along with that, but that's bringing things like intelligent light globes, which are each one connected device that are individually addressable. We look at wireless security systems and wireless IP cameras that are all in a residential environment that were only in commercial spaces, not that long ago. And they're affordable and accessible, and they're becoming commoditized products. But on the industrial side, we see a big thirst for telemetry, for sensors in mining, in manufacturing, in retail, for RFID tagging, for basically instant checkout. So you can just wheel a trolley out and bill your credit card on the way out. So those environments are starting to place sensors which only low data rate, but there's congestion within that spectrum that we need to consider. The 900 meg band is being threatened with a new standard called 802.11ah, which is attractive to telemetry devices because it gives them longer range and some efficiency in terms of low power transmission because they're only sending little bursts of data. But it threatens things like the 900 meg space that we're existing in as is. So that's tour guide applications, and there's cultural impact on cultural events and sites across the world. And DECT LE, which is DECT Low Energy, which is again really attractive for those industrial applications where they can send timely small bursts of data with very low power requirements to send that and keep that link alive. The biggest threat for us from the performance class products comes from Wi-Fi. Anybody heard of Wi-Fi? No? Sometimes called super Wi-Fi. Yeah, the marketing geniuses there, right? So these white space devices are wireless networks that are set up to live in the blank spots and free spaces within the television bands. So for data and mobile data applications, and building larger scale networks that deploy with longer wavelengths and allow for transmission through structures more efficiently than 2.4 gig does, that UHF spectrum is really attractive to the Microsofts, to the Ciscos, to the Nokias who are working to build these types of networks. But what it does is they basically look at the free space that's not being used within those television channels and, we'll take up that space. We'll use it, send data through there.
Wouldn't the TV stations be a bit upset about that? Are they aware of that's going on?
They are fighting it, yes. Who's going to win that battle? Where the shift from viewing habits is moving away from terrestrial transmission through to streaming. So how long before television doesn't exist in the form we know it? 2030, huh?
That's my money.
He's put it down. Taking bets. Yeah.
Probably 100.
You'll be bionic too by then. You'll reach the singularity at that point. So there is development being done by the likes of Microsoft and Nokia to try and play in these spaces. They have done research in terms of coexistence with wireless microphones. They are big users of wireless mics themselves in their own facilities, so they recognise that there is a place for that product that they rely on a day-to-day basis in what they do as a business. But ultimately, they want to push more data down the network, so they don't care how it's done. So they have done some experimentation in having white space devices across their campuses in Redmond, and have created a device that would live inside the rack where the wireless mics live and scan the spectrum that is there and report what is going on in that spectrum back to the white space device. So that what it does is allows white space transmission to get as close as it can to those wireless mics to the point where it starts to create audible artifacts in the transmission. And what this device supposedly will do will send a strobe back to the white spaces devices to say, stay out. There's something going on here.
How's that going to work with ad hoc devices?
Good question. So their push is to get the wireless manufacturers to employ these chipsets into their devices. The downside for us is that spectrum is being used. The idea is that a white space device refers to a centralized database that would be held by an FCC in the States, for instance, or ACMA here, that has logged or registered devices that operate in that spectrum, and the white space device can't touch that. But for low power devices, we are not a consideration in that environment.
So that means a TV station could be selling on their blank areas on to somebody else. Their blank,
I don't know.
Spaces that.
No, well, if they're not transmitting in that space,
But doesn't that belong to them though?
well, theoretically. Well, I don't know. Does
They
it?
buy a license for
Yeah.
frequency, don't
They're actually using most of the space.
they?
Yeah.
It's
Yep.
7 channels, I think, in SDS at the moment.
So what we're seeing in the States is they will allocate one of those channels purely for white space device, and then the white spaces devices will scan whatever's not being used, and occupy those spaces.
So there's quite a lot of activity at World Radio Congress.
Work.
and Roger Bunch, who is the engineer for Free TV Australia, is a very strong advocate for trying to look after the spectrum.
Right.
But he's got his work cut out.
Again, we are our own worst enemy. We are driving this. Sorry?
Channel 7's using it for teletext and others are using it for captions as well.
Okay.
Yeah, so they have to fit all that data in there, 7
Yep.
megahertz of bandwidth. So they've got however many TV channels. It has to fit in that 7 megahertz that they've got. Yeah.
And they use all of it.
Oh yeah.
But it's not the transmitters that are affected, it's the receivers that are affected.
Yes.
Yeah, that's right.
How all that.
Yep.
Hey, they were just dumb receivers, we can't say anything.
No. And this is where this spectral awareness comes in, is that, you know, building devices that are smart and talk to each other and report what's going on. So the question is, well, why don't we just use that damn network that's there already, right? So the problem is that network traffic is inherently non-deterministic. So it's sent out in bursts, and if it gets there the other side, that's great, especially for wireless networks. If we drop a couple of packets, we'll just send them again, and you know, she'll be right. But when it comes to low latency traffic, that really isn't ideal. So we need to look at employing timing protocols that look at synchronization of that data, traffic shaping that looks at the way that data is sent out, not in bursts, but in continuous streams of traffic. And then reserving or ensuring that arrives to its destination in a timely manner that's sort of reserving bandwidth in that transmission. In wired protocols, there's some things that are being done to start this process, but from a wireless perspective, we are not there yet. So it's not to say that the devices in the future don't become network-based wireless transmitters, but there's still a lot of other issues that we need to deal with beyond the scope of one slide in this presentation. But it gives you an idea of sort of where we're heading. Quick wrap up. So the squeeze will continue. We'll continue to get kicked around and have to find new places to play. But the great thing is that it does push us to think outside that square and come up with new ways to solve those problems. And my favourite saying, pressure makes diamonds, you know. If it wasn't for us having these issues, something like the Digital 9000 wouldn't have been created. You know, and the idea is that that pinnacle technology filters down into, you know, becomes more commoditized and used in smaller, affordable product. Questions? No?
There's a lot of stuff there, Jason.
Yes, plenty.
Sennheiser's still working in the hard of hearing area?
Yes, we are, absolutely, yeah. So we're doing a lot. We're actually creating a Wi-Fi streaming product that can be used for hearing assistance. Yeah, so it runs directly to a mobile device, and then that pairs via Bluetooth to the hearing aid itself. And we get equalization at the edge, so it's tailored to the user's audiogram and their response rather than blanket compression and equalization that would happen across an induction loop, for instance. So yeah, we're still in that space, very much so.
I formulated a law in broad science, like that increasing efficiency always comes at the cost of increasing complication.
Yes, but if we can mask that complication from the end user, we've kind of achieved something.
The big change that I see in what you're talking about now, the change that you've made is the wireless mic transmitter is now becoming a transceiver.
Yes.
They're talking to each other.
Yep.
Coming out of my background, one of the techniques that one looks at for data transmission is spread spectrum code division multiplexing.
Yep.
First, okay, it takes a wider bandwidth, but you can spread it and you can maximize that channel by your code choice. And you can put, as somebody said to me about nearly 50 years ago, you can put twice as many users on the system, and all that changes is the signal-to-noise ratio decreases by 3 dB.
Okay.
But in terms of wireless, it its efficiency depends on all the signals arriving at the receiver at the same signal strength, which means that you need a back channel, a fast back channel, for controlling transmitter power. That's always been the operational problem.
Okay.
Apart from that, it's latency and so on. But you've got a whole lot of coding solutions that you can optimise, as we can see with LTE, or for voice or for wideband data, at rates and error rates.
I think, John, we better form a subcommittee.
Several.
You're going beyond my understanding, to be honest.
Was a spread spectrum solution like CDMA ever considered?
I don't think it was for us, no. No.
I suspect, well, I know that there's a lot of work going on in Germany looking at other radio solutions and other means of delivering lots of data with minimal latency. But we're not really privy to the details of what that is, but there's...
I think it's pie in the sky stuff at the moment still.
The military gets first dibs at it.
Yeah.
Well, it may well have come from there, I don't know. But it's there's some interesting stuff going on in Germany at the moment, I believe.
Last question. That was the last question. James, you come out the front. Sure. Well, that was excellent for me. I hope you all enjoyed it too. A very, very comprehensive coverage of A to Z of the microphone spectrum and the links for it. I'd like to thank James and Jason for coming down and giving us an excellent presentation. You just right at the end mentioned Bluetooth. I was going to ask, but you got it in there at the end. I don't know what you're doing with Bluetooth, but there's quite a bit of scope there. Anyway, I'd like to thank you on behalf of the committee of the AES Melbourne section. I'd like to give you a little token of our esteem.
Thank you very much.
And that's to make sure that you might come back sometime. Okay.
Well, we'd love to come back.
Absolutely.
Thank you very much.
It's been
There's
great.
probably a few questions if you want those. It's now.
Very happy to take some questions from anybody. And
Informally now, because
Yeah.
we could probably say that the session has been closed.
thanks everybody. I know we've been here for a little while tonight, but thanks
that's
for
fine.
staying with
That's
us,
fine.
and hopefully it's helped understand a little bit about the future of wireless mics in
It's been
particular,
excellent.
and
Thank
a little
you
bit
very,
about
very
where we've come from. So, thank you.
Yeah, thanks for having us. It's been great.
Indeed.